Hey, how you doing? This is going to be an explanation video for our opposition who did not understand my previous video on how the triangle debunks the globe model. Um, I started my last video with this diagram here. It is a diagram of Al-Biruni's method for measuring the supposed globe Earth's radius. Um, there is some writing down here on it. I will just go through it quickly. An illustration of Al-Biruni's method of calculating the Earth's radius. One can observe that the Earth center 0, which is here, um, the mountain peak A, which is up here, and the horizon C, which is over here, form a right-angled triangle. Mathematically, angle COA is the same as here. This is this symbol here. Can't remember the name of it. The angle of same as the angle of dip from the mountain peak to the horizon. Using trigonometry and the Pythagoras theorem, one can solve for R. So this is how Al-Biruni supposedly measured the globe Earth's radius. Now, in my last video, I focused on this area, okay? And I pointed out that that was not a triangle. And our opposition didn't seem to understand why I focused on that. I pointed out last night how this was a problem. This area here was a major problem. And they didn't seem to get it. They accused me of being incorrect. But I'm going to explain now how I'm not incorrect, not even remotely. So, as I said in my last video, triangle. This is the definition of a triangle: a plane figure with 3 straight sides and 3 angles. This is a triangle. This is not a triangle. But the problem is they were focusing on this diagram and they were missing the simplicity of what I was talking about. You see, they're focusing on this here as 0, A, and C. Okay? So they're focusing on that right angle triangle and this other right angle triangle here that's meeting it. So there's a triangle, a right angle triangle going from A down to 0, 0 to C, and C back to A, and from A out here and down to C, okay, and past this spherical shape or circular shape. But the problem what they're not understanding is this. It's very, very simple. This here, right, this straight line out here from A, this is what's known as the astronomical horizon. This here, this straight line down to C, right, this is known at C, this is known as the geometric horizon. Now, neither the astronomical or geometric horizons exist. They don't exist. So Al-Biruni, right, used 2 horizons that don't exist to somehow calculate the radius value of the globe Earth. He had to pre-assume first that he was already on a globe. He had to pre-assume that he was going to be able to supposedly measure this radius. And then he had to pre-assume the existence of 2 horizons that don't exist. The astronomical horizon is just your straight line horizontal view, eye line view, from wherever you stand, regardless of your elevation. That's your astronomical horizon, straight out from your eye line view. That's basically all there. As a basic description, that's all it is. So it's really just a way of describing your straight line horizontal view from your eye line. The geometric horizon is based on us actually living on a spherical surface of a geometric size. So these both horizons don't exist. So Al-Biruni first had to pre-assume he was on a globe, then used 2 horizons that don't exist, because we've never ever seen, no one can ever see the geometric horizon, as it's purely mathematical. Even our opposition tell us that you can never see it due to the refraction. And the refraction they're talking about is the refraction that's based on the R value, called standard, also known as terrestrial refraction. it's all based on the R value. So you can't see the geometric horizon because of the refraction that's based on you actually seeing it in the first place. So to calculate standard or terrestrial refraction, you'd have to first be able to see the geometric horizon before you did anything else. So because you need that to solve for R. So Al-Biruni had to pre-assume the existence of two horizons that don't exist. And our opposition now say that we can't see that the first one is just, you're never going to see it. It's just purely just a straight line, eye line from wherever your elevation is. That's all it is. It's just a description. And the second one we'll never see because it's purely mathematical. But yet we are told that the refraction that's based on the R value, and the R value is calculated by someone actually seeing this supposed geometric horizon. We are told that we can never see the geometric horizon because of this refraction that is based on us actually seeing it in the first place. So it's a circular nonsense. Okay. So why was I focusing on this part here not being a triangle? It's very, very simple. You can throw out the astronomical horizon and the geometric horizon and the R value, and you can throw out the standard and terrestrial refraction because none of it is real, right? What did Al-Biruni use? He used, when he was doing this supposed horizon dip angle measurement, he used an astrolabe. Now, the astrolabe is the is the predecessor to the sextant. Okay, so just going to come back to that in a minute. Right, back show this is sextant. Okay, so I'm just going to read a bit of something. 1 second now on the sextant. When you use a sextant, when you use a sextant to take an angle to the sun, moon, or stars, the very first thing that you must do is take your observation elevation above sea level into account. So if you're 100 foot above the ocean or 4 foot above the ocean, you must take this added elevation over sea level into account in your final angle calculation. So basically, you must make a right angle using the ocean as a flat surface or horizontal baseline for your right angle, and then take your angle off of this horizontal baseline to your chosen luminary in the sky and its angled height above the horizon. This means that a right angle must be made using the ocean as your flat baseline before you can take an angle between the horizon and your chosen luminary. This rule is true for sextant and its predecessor, the astrolabe. Okay, so just to show this here, right? As you can see, this is the horizon. This is straight line from the horizon to, let's say, they're using Polaris here, just a star. And they're using the angle between the horizon and the angle up to Polaris. But that angle is coming straight back in a line, right? With the pre-assumption that this man's eye line is starting at the horizon. So all angles are taken off of the horizon. So all angles, every luminary is taken off of the horizon. So if he's 10 foot above the ocean, he has to take that 10 foot off of his final calculation. His final angle calculation has to be taken off of that 10 foot. That 10 foot has to be taken off his final angle calculation. If he's on a boat and he's 10 foot above the water, when he's using the sextant to take an angle to a luminary, he must take that 10 foot he is above the water because he's standing in the boat off of his final calculation. So that's how you use a sextant. Now, that is not what happened here with Al-Biruni. Al-Biruni didn't do that. Al-Biruni pre-assumed it was a globe, right? And the evidence that he pre-assumed it was a globe is because he took a dip angle and didn't take away he took a dip angle to a supposed geometric horizon, which was just any horizon on the day, right? Because the horizon is an optical effect. It moves with the weather and elevation all the time. You can hold the same elevation, and within an hour, the horizon can be closer or further from you. It depends on the weather of the day and the atmospheric effects of the day. That's what it depends on. So Al-Biruni never took his height on the mountain into account when he was using the astrolabe. He just purely used the dip angle. If you take B here and you bring a straight line out from the base of the mountain and a straight line out from A, which is already there, but if you take another parallel line out here, then you have two different parallels, or sorry, two different horizontals. So if you're above the ocean, you're going to be, in any way, you're going to be above the horizon. So all Al-Biruni was doing was taking a dip angle to an horizon that he knew he was above. That's all he did. And then he used that and called it, and called it the geometric horizon because it suited what the calculations, the Pythagoras calculations, and what he already pre-assumed. It suited and what was pre-assumed by Eratosthenes. It suited him to use that or within a percentage of that, and make and calculate some kind of a radius similar to what supposedly Eratosthenes did, and Pythagoras, I'm sure, spoke about, because it's all mathematical. It's purely made up, and it all comes from Pythagoras. Other people just pre-assumed it after that, and that's what Al-Biruni did. There is no geometric horizon. There is no astronomical horizon. Them things don't exist. There is only one horizon, and that is the horizon we see, the apparent horizon, that moves with weather, will move with weather and elevation. That's what will make that move, and it will constantly move all the time. You can keep the same elevation. It will move closer or further from you, sometimes really far from you, sometimes really close to you, depending on the weather, right? If you hold the same exact elevation, it will change. So how can it be geometric? It can't. So how could Al-Biruni get an angle to a geometric horizon he couldn't see? He couldn't. It was impossible. So back to this, right? This is a right angle triangle, right? So the right angle is the important part, because as we saw earlier with the sextant, all sextant angles are taken off the horizon, the very thing that Al-Biruni didn't do. So that's why this is a triangle and this is not a triangle, because this would have to be, because the way Al-Biruni went about it is completely wrong. That's not what you have to pre-assume a globe and pre-assume all kinds of nonsense to make that work. This is not a triangle. A second now. Let's go back up here a second. Yeah. Our opposition are focusing on these triangles here that are based on two horizons that don't exist. So if they don't exist, you can't use them. It's very simple. Al-Biruni didn't measure a radius. He calculated a radius based on a pre-assumption and mathematics he probably already had. Or it's claimed he did it. I didn't know Al-Biruni. I didn't know Eratosthenes, but it's claimed that's what they did. But there is no horizon that matches the geometric horizon. There is no horizon that matches the astronomical horizon. There is only the horizon we see. And if you're above water, if you're above sea level, then you're above that horizon. It just doesn't always appear that way because the horizon can be so far away from you, can stretch so far away that they keep, because it's going across a flat plane, it keeps stretching out and out and out. So if you measure a dip angle to it from an airplane or whatever, you're 6 miles in an airplane, you're 6 miles above the ocean. So you're 6 miles above the horizon. But the horizon can be so far away from you, it can appear halfway up the windows of the airplane. You look out the windows and halfway up the windows on the other side, there's the horizon. Why is that? Because it's on a flat plane. But you can make a dip angle to that horizon and you can add in a load of pre-assumption and you can use two completely invisible horizons that don't exist. And you can calculate R if you want. And you can calculate it, it depends on where the horizon is, you can calculate all different sizes of R. But you won't be dealing with reality. This is not a triangle. This is a triangle. This is not a triangle. This is a triangle. And when we deal with reality, this is what we use. a right angle triangle. Thank you.